I'm moderating the session. So, you know my name, so I won't repeat myself. Dr. Satish Kumar, hmm, uh, founder and president of Alliance for Energy Efficiency Economy. I request you to please come? Satya, you should stay here. Um, this is a AEEE supports policy implementation and is an energy efficiency market enabler and not-for-profit motive. We have Karthik Kumar from Saint-Gobain. Saint-Gobain, many of you know that this research park that you are there, tomorrow you'll be going around, is a 1.2 million square feet, and our primary tenant, what is called anchor tenant, is Karthik Kumar. And Karthik Kumar, Saint-Gobain actually does a lot of work on glass, and particularly the glass which ensures that heat coming into the building is minimized, and he is working on heating and cooling. We have a youngster named Ankit Poddar, who came out of the system and is an incubated company called ZB. He started with this cooling, and in fact, most of the buildings that you will see here are actually cooled by him. The technology has been developed by him. And finally, we have Bhardwaj Ramakrishnan from Applied Materials, and this is pretty much our team. We have an extra chair. I don't know what for, or somebody is missing. Satish Kumar is here. Satish Kumar is here. Karthik Kumar is here. Ankit Poddar is here. Where is Bhardwaj Ramakrishnan? Oh, there you are, Bhardwaj. Okay, so we have the right chair. This session is the last session of the day. Just to remind you people, the students from our partner engineering college who are here are supposed to meet me in the next room. What is that room called? Amphitheater at 6:30. We'll try to wind up by 6:30. May spill over a few minutes. After that, we have the dinner out here, a gala dinner. So in the 6th floor, I hope all of you will stay. So before that, we'll get on to this session. And I request now, not Prasatya, but the rest of the people to speak for about 6 to 7 minutes, maybe 8 minutes at most. I'll cut you out. I'm very bad at that. And give an introduction on this whole concept of heating and cooling. You can take off from what Satya mentioned, or you can just do whatever you want, and then we will have a discussion and question and answer. So we start with Satish Kumar. Yeah, please.
So good evening, everybody, and thank you, Professor Jhunjhunwala, and thank you, Rahul, my friend, and IESA for extending an invitation. I was delighted with the presentation that Satya, you made. Cooling is a passion for me, and Professor Jhunjhunwala talked about Alliance for an Energy Efficient Economy, so I'll just take maybe 15-20 seconds. So AEEE, which is Alliance for an Energy Efficient Economy, is an industry association, and we work on two sides. One is on the policy side, and one of our flagship contributions recently has been the development of the India Cooling Action Plan. So this is a policy document that Ministry of Environment, Forest and Climate Change talked about, and which looked at the entire economy and talks about, I think, what is the potential of cooling and refrigeration that India currently has and what it will have over the next 20 years, because we took a 20-year view. Also, we are focused on creating a market for energy efficient product. So we have about 45 member companies. It's a mix of like multinational companies, Indian large companies, as well as small and medium-sized startup companies. So I will talk a little bit, I think, during the course of my presentation. But let me start with a quote. And I like this quote. In fact, I posted it on my LinkedIn thing. And there is a lot of discussion that has happened, which is happening on the supply side. And rightly so. I think that's very, very important. But let me start with this quote, that fire can be used to warm ourselves on a cold night, but it can also be used to burn down the house. The same is true of electricity and nuclear energy. Making energy available for human use is an important accomplishment, but learning how to use this energy well is at least as essential. And this is by Mihaly Csikszentmihalyi. He's a University of Chicago, pretty well-known professor, and he has this book in Flow. So that's one thing. The second thing, I will go back to the quote that Professor Jhunjhunwala and Mr. Murugappan also used, that there is I think there is a lot for everyone's need, but there is not a lot for a single man's greed. And this concept of simple living and why India should espouse that, I think that's also very, very important. And I'm talking about these things because I feel that when we are talking about how much energy India needs, we should start with that how much energy I think is really required to cool our homes, to run our appliances, to run our cars, to run our industries. And just having a skewed view that we need to produce more, or generate more will not allow, I think, the efficiency to take the importance that it sometimes deserves. With that, I would also put like 3 frames that I want to use, and in two respects. So first thing I'll say, we have this glass bottle. Suppose there are like 100 holes in this glass bottle. Just visualize a picture. What will be your reaction? So there are 2 responses. You will say that, hey, I need to plug these holes, or I need to use a different glass of bottle, or I'll put more water in it. Let the water flow. I have enough water. I'll just keep pouring more and more water into this bottle. So this is just an analogy that I am giving just to make the case that we are at a very critical moment as far as energy transition is concerned. And both the demand and the supply side are very, very important here. Okay? The other example, we are in this IIT Madras Research Park. There are many buildings. I was visiting, Karthik was with me. He was giving a tour of the St. Goma Research Center. And I was saying that I would like to use a construct because I look at cooling not as just a technology fix. I think that's my main point that I'm going to talk about. We have a very simple construct where we talk about lean, mean, and green. And I myself, by the way, I'm myself an architect from IIT Roorkee. Then I did my PhD from Carnegie Mellon University in building science. And so I am a kind of like same alma mater as Rahul. And then I worked as a scientist at Lawrence Berkeley National Lab in their building science division. And then I moved back to India about 16 years ago, because I found India more exciting, and I said that I think there's a lot of action, there's a lot of impact that could be created. So just a brief background about my background, and we talked about the interdisciplinary nature of the energy transition and other things that we are talking about. So the thing is that before we talk about whether we are going to use seawater air conditioning or heat pumps or like vapor compression, I want to ask this question, that how much cooling is really needed in a building? And that's something that we want to call lean, because you can really drive down the cooling that is needed to provide optimal thermal comfort through, I think, a building design, insulation, shading, high performance glazing, a lot of these things that we are right now teaching through another program, which is Solar Decathlon India, that IIHS and AEEE is doing, where we are talking that how can students be trained not to go straight away to technology, but to use the first principles, and Professor Jhunjhunwala will appreciate it. I'm sure that I think even when we talk to students, we talk about that start with the first principles. So start with the conduction, convection, and radiation to see, I think, how much cooling load is going to be needed. Then you talk about which technology, and Satya did a wonderful job, I think, in terms of talking about the different technology. And finally, so that's the mean part, and finally, use renewable energy to actually meet the requirements. But these three things have to be done in this order. You cannot say that, hey, I'm going to do renewable energy. My building is very leaky. I'm going to put more and more cooling into it. If it's leaking, doesn't matter. I think, and this is also a very important point, because through efficiency, you can involve the citizens of India, through the businesses, through the to the government with the policies. So we also talk about establishing or developing a culture of energy efficiency, where right from customers to businesses to government, everybody says that we need to design our appliances well. We need to design our buildings well. So that's, I think, the first point. And we talk about this culture of energy efficiency that, and lastly, I will talk about the how to achieve this net zero energy paradigm that I think a lot of speakers before me have talked about. This is something that we are looking at accomplishing. I think India has set a goal of 2070 as part of Panchamrit. But the journey, because it is such a difficult journey, needs to start right now. And we have to do everything in our powers to ensure that the businesses are coming out with a lot of technology, products, and solutions, and we create the policies that encourages the adoption of these products, because otherwise India will always get the substandard product. Trust me, there are lots of wonderful products, but a lot of companies, when I was working at Schneider Electric, I think for my 5 years, they said that we cannot sell our most efficient products because of the costing issue and because. So how do you incentivize the adoption of these latest and greatest technology? I think to reduce the energy demand is also something that is very, very important. Thank you.
Thank you, Karthik.
I'm Satish, sorry.
Oh, sorry.
Yeah.
Thank you, Satish. And well, I was actually going to move to Karthik. I think he is going to talk about how to not have leaky buildings. Leaking out, or this time, the heat leaking in. So, Karthik from Sengoben.
Yeah. Hello. Thank you. Good evening, everyone, and thank you, Professor Junjunwala. What I'm going to speak is from the. He had given a good example bottle just to equally have the metaphor for the buildings. So, firstly, I am from Saint-Gobain, which is a 357-year-old company. We are in 75 countries, and in India, us mostly by glass. And I'm going to give that example of glass. So for what a lot of what Dr. Satish said, we are in the same agreement that the sustainability or carbon footprint comes from two elements. One is the architectural element, another one is the material element. Coming from the fact that in architectural side, a lot of things depend on how the building envelope is designed. I was new to it that even the kind of wall facing the south and west would be more heated than the wall facing the east and north. You'll be kind of surprised that these designs could help a lot in managing the light and heat balance. Now, Saint-Gobain as such has committed to net zero carbon by 2050. So in that sense, our carbon footprint calculations have begun with basis from 2017, and we found that 40% of our carbon footprint is associated with building and construction. So in that aspect, 28% is primarily at the user level, which means if the 12% is of the carbon footprint is while constructing, and 28% of our carbon footprint is while the use of HVAC, and other systems which are important for us to understand. Now, if we go to that granularity of 28%, the carbon footprint, we divide that into two parts. One is the element that, okay, there is a carbon footprint, and the other one is, of course, what is comfort. We will not compromise on comfort. We will always have the HVAC, the heating system are all part of our comfort system. So if I were to talk about thermal comfort, we will have that. And to have that, primarily our role is to keep the insulation intact. Whether we are going to cool or whether we're going to heat, we're going to have the insulation system in place. India has about 5 climatic zones. And whether you're talking about hot, humid, or cold, or systems, basically we are looking at an element where how much can you preserve the energy which we use to heat or cold. Yeah, in that context, I'll use the example of glass. We use glass facades today for what we would call as light and sustainable construction, which means today instead of the brick and mortar, if you replace it with the glass facade, you get to have light, but you also tend to have heat, right? Then that's where the new technologies have to evolve. We start developing a new kind of glass, which is called low-E glass, which is like coating a very thin layer of silver, which could just be opaque to the heat, but transparent to the light. Kind of a thermos flask, literally. It's like, if you are looking at a double glass system in a vacuum and the reflective part inside, it kind of reflects off the heat, which is the short UV and short IR and the long wave IR, which is kind of things which we are working on in various coating technologies. And then what happens? Literally, based on where I place the glass, I could either cut off the heat from the sun, or I could keep the heat generated. I'm talking in the cold countries, to keep the heat generated intact inside. So that becomes the kind of an insulation which we are working on. And that's, in addition to that, we have other things like glass wool, gypsum, and other components, which also is part of our portfolio, which helps us to be in part of the light and sustainable construction. That's part of it.
Thank you, Karthik. Next is Ankit. He does something different. Once you have heated the building, he cools. And what was most interesting is that I remember before he started the company, actually there was a problem that I used to face. That we used to have in our incubation center in RTBI. I used to sit in a small conference room at one end of the room. And either that place will be too cold or will be just too hot. Could never make it the right temperature. I used to almost come there and shout, what is this? It's made so cold, I'm shivering, or it is so hot. And I was told that, well, by the time the chilled water, the air cooled by the chilled water travels from one end of the building to other, either it is too hot or too cold. So I actually asked him to actually design something such that everyone gets the exact amount of cool air. Ankit, can you introduce yourself? He's a founder of a company called ZB Technologies.
Thank you, Professor Ashok. And it's a privilege to be here and talking about what we do to really make building more efficient. It's also, I feel very proud to say that Professor has been my guide to get my master's done on how to make building more efficient. So thank you again for having me here. I would, as I'm a founder and CEO of the company, we really have to do business. So just to give some statistics, we have 50,000 buildings in India, which really needs air conditioning to become as efficient as possible. And almost 8 to 9% of the total power that we consume in India is actually going into commercial buildings. So this is a really important sector where we have to really start looking at how to make it more efficient. Now, in every building, we have been seeing since morning that almost 40 to 50% of our power in building is actually going into air conditioning system. Let me just take a minute to explain how this air conditioning system actually works in a building. So there is a plant which generally most of us do not see somewhere in the basement or something in the terrace, where it's called chiller, pumps, and a set of cooling towers that is basically giving you chill water. And then every floor you have a machine called air handling unit, which does the heat exchange and ensure that the cold air is given to the respective office space. So there is something called as a generation, which is chiller and pumps and cooling tower, and distribution, which is air handling unit and ducts at the floor level to give you the desired cooling. Now, if you talk about efficiencies, let me just give you a few examples of where we are really wasting energy. First is, as a human, we always need air conditioning to make ourselves comfort and, not to give comforts to the table and chairs. So many of these large commercial buildings, we have seen many of the times that the offices are not fully occupied. To To give them numbers, let's say we have in our homes, we use 1 ton, 1.5 tons of air conditioning, but in offices, we generally have 20 tons, 30 tons of one single machine that is giving the cooling on an average. But if you see the occupancy level that we have in offices at different times of the day, average cooling required is only 5 to 7 tons. But the way systems are designed, we are running 20 tons, 25 tons of air conditioning system, and actually giving coolings for tables and chairs, which is not required. So that's actually a criminal thing to do because we are wasting so much of energy over there. That's first point. So what we do is we try to identify where are people sitting and ensures that the coolings is only given to that area where people are sitting in the office. That's one point. Second, we always try to overcool. We feel that when I set the temperature at 22 or 21, I'm running the air conditioning in a much more efficient, and we feel better. As an young guy, of course, when I see the temperature at 21, I feel happy, okay, fine, I'm getting better air conditioning. But if we look at the thermal comfort for every individual, 25 to 26 degrees is actually you feel comfortable with a little bit of draft on your skin. So you really do not need to cool the temperature to 21 and 22. I'll give you an example, a small experiment that I did few years back with the AC that I have at my home. The 1.5 ton of AC that you have in your room, if you set your temperature at 21, generally with the remote we keep changing, so we have a perception that I am setting at 21, the air that is coming out of the AC is 21. That's not the way it works. It's like when you are setting at 21, and unless your room temperature is reaching 21, the compressor, which is the power guzzler, will keep running. And the air that comes out is always at 11 to 12 degrees Celsius. Now, practically, you will never reach 21 degrees Celsius in your room because of the heat exchange and all the thing that you are having. So essentially, what you are doing, if you are setting at 21, the 10 hours or 11 hours, the AC that you are running keep running throughout the night. Now, every hour, I'm a businessman, so every penny matters. Every hour, you spend almost 10 to 12 rupees as an electricity cost for the AC that keeps running. Now, imagine if I set at 21, we are spending almost 100 rupees per day to cool my room, which basically I use a blanket and sleep off. But if I set the AC at 26 degrees Celsius, which I've been doing that for the last 3 years, I'm spending only 15 to 20 rupees every night because the AC runs on an average for the 10 hours, only for 2 hours, because the moment we reach 26, the AC cuts off. And it gives comfort with the fan that you run. So same thing we have started doing in commercial building where we have a mandate to not decrease the temperature below 25, and we have seen massive savings that comes here. So one is, of course, not cooling the area. Second is making the optimal temperature across the offices. Third is a lot of more deep thinking, like when we do the heat exchange, are you doing a proper delta T management, the chill water distribution that is happening? All these are collecting a lot of data, seeing where are efficiencies, gaps and all, and building algorithms to make sure that things are really working efficiently. Last is, I'll give an analogy here. What really happens in this kind of machines, like cluster of machines where chiller, pumps, cooling towers, AHUs. Let's imagine, I'm sure a lot of you have actually gone to some bands and orchestra. Let's say there's a set of orchestra sitting here with a guitarist, a piano, a violinist, and each of them have individual masters. Ultimately what you will get is a noise, because one master is actually telling piano how to make it run. The second is violin. The third is drummist and all. So it's all noise that you will get. But actually, if you see how they operate is one master give instructions to everyone that how you have to work, and what you get is out of that is a soothing music. The same thing today happens in building is, for chiller, you have one master, that keep giving instruction to chiller how you have to operate. Same for cooling tower, you have a separate master card. For AHU, you have a third different kind of a master card. So it's actually not very efficient way of managing the machines. What we have figured out is get all the data into one platform, and that platform become the master for all these machines. So we are synchronizing your air distribution, your AHUs, your chiller, your pumps, your cooling tower, linking it to your occupancy pattern, linking it to your weather pattern, linking it to a lot of different types of data variables, and making sure that machines runs very efficiently.
I'll now move to
Thank you.
Bhardwaj Ramakrishnan of Applied Materials. He has worked on many things, but including clean tech and energy efficiency. So,
yeah. Professor, I just wanted to add one point to what Ankit actually said. In our building science, we have understood that a fan with no AC is far more comfortable than with lower temperature.
we'll talk about it.
Okay, perfect,
Please.
perfect.
Thank you, Professor. Thank you to IITM Research Park for inviting me. So it's been a great to be back in the IITM campus. So I'm Bharat Ramakrishnan. I've been working in the semiconductor space and clean tech space for close to 20 years. So Applied Materials, as some of you know, makes equipment for the semiconductor industry, display industry, and solar industry. So I'm part of the office of the CTO, where I've had the entrepreneur hat, and essentially I create startups, and that's what I've been doing for the last 10 plus years. So what I do is I focus on ideation and focus on how to actually incubate them, talk to the customers, partner with various entities. And in that aspect, I've partnered with IIT Madras, and it's a great team at IIT Madras. I just finished a project with one of the professors yesterday. We are looking at another program with one of the professors here. So it's been active collaboration with academia and research institutes. So the entire step is from ideation all the way to commercialization. So today morning, Professor, you mentioned about...
Can we focus on the topic for this session, please?
Yeah, definitely. So from an energy efficiency perspective, some of the elements that I've worked on beyond just the heating and cooling, more primarily on the energy efficiency, is if you look at LEDs, 10 years back, we're looking at material science. So if you look at the IITM community as a whole, MOCVD by gallium nitride is something that we did. So that's one area that's already 10 years later has been fully commercialized. So if you look at other areas that are ripe, are thermoelectrics, power semiconductors is one area where its silicon carbide is actually coming up, but there's still a lot more high-value problems that could be solved. So those are some areas that could be done. So I was looking at the energy efficiency part of it. So one of the key areas which one of the earlier speakers was addressing is about the data centers, right? So data centers, 12 years back, I worked on making data centers very efficient, but with all the demand, with all the data centers increasing exponentially, there's still a constant need for making data centers really efficient. So if you look at from material science perspective, again, looking at the professors and students and the community at large here, there are a lot of low power electronics that are necessary to actually make these data centers less power hungry. So you don't need to cool them as much as they want. Currently we are cooling. So that is one of the areas that we should constantly think of. And this also relates to the last slide Professor had in your, and then also the one from Schneider Electric that Satish mentioned. What is really needed? I mean, the demand will definitely be there. I mean, there are a lot of industries that are power hungry. We need to create industries for various reasons. Energy security, do we really need to generate a lot? I was looking at the news yesterday. ONGC is installing a 1 gigawatt solar in Rajasthan. There's another entity, 1 gigawatt in Assam. Coal India is doing 1.19 again in Rajasthan. So the key here is, what do we really need? Energy efficiency is really important. The panelists have talked a lot. And then there are a lot of other low-hanging fruits which really need to be done from a policy perspective. Yesterday, I grew up in Chennai and I used the public transport quite a bit. Yesterday I went from Adyar to Chetpat, and if I look at that, it was a 50-minute ride, and then it was raining, but the bus was, I would say 5 to 10 minutes was standing still and burning a lot of gas. So essentially that's just one part of it, and then there are several cities, several buses. So if you can, and I drive a hybrid car and I get twice the gas mileage. So this is definitely an area where technology exists today. So there's, from a policy perspective, as Satish mentioned, this is a perfect area where we can reduce the energy consumption. Energy security is really key. Professor mentioned about Sri Lanka and India. We have coal, so coal is still really good, but that doesn't mean we should burn coal and generate something for everyone to waste at their home, right?
Thank you.
So those are some of the thoughts.
Thank you very much. Thank you. I think you heard some wonderful talks and brief introduction. I will start with a few questions and then open it up for the audience. First, as was mentioned by you, Karthik, one of the concerns of mine is that if you saw the graph I put in the morning, the air conditioners used is just going up exponentially, and it is only the beginning. As GDP goes up, in India it is going to go up drastically because India is a hot country. And as soon as you can afford air conditioner, you try to put it in home. That will mean huge increase in energy usage and will result into more GHG. I have a question. Comfort. We all want comfort. The reason we want an air conditioner is we want comfort. In North India, in dry parts of the country, a water cooler can give you very good comfort most of the time. In a place like Chennai, which is high moisture, it does not. Actually, a fan could do very well if you could remove some of the moisture. So my first question to all of you, what is possible in terms of taking a room, in North India, as I told you, water cooler will work. Here, can we remove moisture? What is the easiest, lowest energy cost? Can we remove moisture a bit and use fan and open our windows? Can we live in Chennai and with that? So that's a question anyone wants to answer one by one?
So let me stop where of course, Dr. Satish, before 1 minute is that whenever we lived in life without AC before, what I meant to say was...
my home doesn't have AC.
Yeah. So if you are looking at the fan, that gives a lot of comfort. What we are actually saying is the body heat gets immediately, quenched, as he said, if you really get your airflow over it. Now, in that context, it's important to understand a difference between latent heat and the radiant heat. Dr. Satish, you have something to say, then I will come back to a point which is also another possibility.
Question, if you look at India's peak demand profile, every year we hit peak demand around end of June or early July. And it's not just, I think, because of the dry temperature heat, but it is a combination of both latent and sensible load that. And according to our calculations, about 25 to 30% of India peak demand, even right now, is coming from cooling. So if it's like 210, so about 50 gigawatt, we are saying it's coming from cooling demand. And this is based on the fact that we have just about 8% penetration of room air conditioners in homes. Coming to your point, I think there are technologies and people have tried. So there is a way, like desiccant wheels have been used, I think, which is, I think, when you pass it here, it absorbs and removes the moisture. And then I think that can do the trick. Sometimes there is direct and indirect evaporative cooling.
We know these techniques.
Right.
Desiccant we know, but I have not seen it being used. Is it possible in the next 5 years, next 3 years, to really build something that I put a desiccant? See, particularly in Chennai, 2 months in a year, maybe 1.5 months in a year, are bad days. Fan is not good enough because there is too much moisture. Is it possible for us to crack that? Satya?
It certainly is. So far, it's not matured because the vapor compression systems have really massive economies of scale. So it's always been cost, but technologies like Dr. Satish said do exist.
But highly energy consumption.
Yeah,
Immense.
we can definitely put something. And recently, I think 2 years back, there was this global cooling challenge competition, out of which the winning entries essentially had a combination of desiccant and some membrane. So it certainly is possible. We can build a device within 2 to 3 years if we put our minds to it.
Is it possible, even if you want to have an air conditioner, you can have a dual mode, one mode in which either works as a cooler in places where moisture is low, or works as a desiccant removal plus a fan when the moisture is
Doctor, it exists
high,
today.
or
It exists.
in worst condition, you turn on the air conditioner.
Doctor, it exists today. There is a dehumidifier setting which I use today.
Can we make it low cost enough and make it popular in
Yes.
India?
There is a dehumidifier setting which I use at 28 degrees and I feel very comfortable. It's at only all it does is remove the
Humidifier you have?
It's a normal AC which has a setting which is the dehumidifier setting.
But it is still vapor compression.
It's still vapor. Is there a way by which I use much less energy?
Yeah, I think the global cooling challenge winners, the technology exists. We do know how to do that. We just have to build it.
So there were two final awardees, the GRI and as well as the Daikin. And they both used the same thing that you talked about, Professor Junjunwala, that when the humidity was low, they were running it as an evaporative cooler. And when the humidity got high,
So,
they
so
started
there are large number of young students out here. I think a problem that we give it to you, and we probably will have a challenge. What do you call it? That hackathon sometime. Invite all of you. How to remove moisture and in a room and use a fan to make it extremely comfortable. So that's one thing that I want to talk to you. Before I go on to the next question, I also open it up. Anybody has questions, please raise your hand so that we'll give you turns. Yes, go ahead, and please pass the mic.
Yeah, this is more of an observation than a question. I feel like the usage of the air conditioners is actually going up because of the use of air conditioners.
Because of a?
Because of the use of air conditioners. What I mean is, the neighbor next door is actually having an air conditioner, and then he actually puts it hot air into my house, and then it becomes so hot that I actually add another air conditioner, right? And then I believe that the summers are hot more now because of use of air conditioners and because of this additional heat that is being put in the air. And I don't know how much it is. I would like to
Thank you.
get the view from
Thank you to use vapor compression technique or tomorrow something else. What Professor Satya presented to us, that it actually heats up one side, cools up another side. And if we can use both heating and cooling, then we can have a coefficient of performance of 6 or probably more. Now, first thing is, at any home, we require both heating and cooling. We require heating for maybe our bathing water, for washing dishes, for washing clothes, and for kitchen. Cooling we require because it is too hot, and therefore we need to cool the rooms, we need to cool the refrigerator, and chiller. Is it possible for us to design a system which can, for a home or probably for a group of homes, do both and get a COP of 6, 7, 8, 9, 10? One problem will be that heating and cooling may not be simultaneously used. It may be time offset. The time offset is not such a big problem, because if finally heating and cooling is available in terms of hot water and cold water, we can put hot water in some kind of a thermal storage, which we do in our geyser, and cold water in some kind of a thermal storage, and then use it. Is it possible for us to take up a challenge and design home or a group of homes which can do both of this? I'm talking on one side, cooking. We need hot water. If I start with 60 degrees centigrade hot water for cooking, all my cooking energy requirement will go down significantly. If I use 60 degrees centigrade or lower to wash my clothes can be washed. For washing my utensil, I can do a mixture of that hot water and cold water to get the temperature that we want. Chilled water, we use to do refrigeration and air conditioning. Is that possible to design homes like this? And in what time frame? I want to hear from each of you.
The only challenge we normally face in a place like India is the demand for both are heavily skewed towards one side. So there's much larger demand for cooling than heating in some places. So that's one of the challenge, but partly, yes, you could address some utilization of hot water. But rather, I think the major usage challenge that we would face is there is not enough demand for hot water. We would be producing
that has to be calculated. We have to see, because for cooking, washing, bathing, everything is done then we have to calculate and see. Second, we can then not use, we can try to sort of say how to use less cooling by actually removing moisture. Can we really do this? Can we think of 100 students working on this? Can we create hackathons on this? Can all of us, all the companies sitting out here?
One of the use cases that the global cooling challenge people also used is part of the heating is also required for cooling. So especially when you use these desiccants, you need to regenerate the desiccants. So you need heat recycling.
Anyone else? Yeah.
I think doing this at a home level is a much tougher challenge in terms
Group of homes, 10 homes, 20 homes?
Yeah,
a
so
flat
maybe
system?
neighborhood, maybe I think large buildings, it becomes a little easier because then you have diversity of loads and you can probably think. So it's
Why can't
probably
we
by
take up challenge
physics.
like this? Why don't we take up challenge? Why do we always have to follow the West? Why don't we take our challenge?
I think this will be a massive contribution. I think if students, I think next generation of leaders, I think can come up and do something like that.
Yeah, I think this is a great idea. I think from a perspective
Applied
of-
Materials has already agreed to sponsor this challenge.
So from a perspective, I think if you look at the customers and then prioritize by the need, right? Residential is definitely one, but since some homes are all not designed uniformly, right? I think the best way from a customer perspective would be to target like research parks like this or hotels, for example, right? Where they do heating, they do cooling, and then they're bigger scale.
Sure.
And then that
We are
creates
already
a-
doing it here. But I want homes also. And we want to come to the industry. Sir, Ankit.
No, sir. It's certainly possible. If we, I think we all youngsters should. I have learned from Professor that nothing impossible for us. So what Professor is saying, that concept, absolutely it's possible. Theoretically it's possible. Practically we can do it. Maybe after, as in when we start experimenting, 6 months, 8 months down the line, we will have hiccups of how do we commercialize, how do we meet the customer expectations, productization. But I'm sure this is certainly solvable.
Yes, sir, you have anything more?
For me, actually, I go with what Professor Satya said. In the sense, for a lot of the India is not in the humid climate. Even though hot and humid is there, for us, there is a challenge as well in hot and dry climate as well.
So if it's not a humid climate, then it's a very simple. We use a
right.
water,
So in that sense, there is a
water
reason.
cooler. What is it called? Not water.
Then the challenge becomes a little bit, in the context of what you said, possible.
The mix.
That makes sense.
We design. What is it called? That desert cooler. Desert cooler.
Then what you becomes then otherwise if it's the coastal area then it becomes.
Any other question from the audience? Anyone? Yes, sir. Rahul.
But this question is common for any of the panelists. I think in the morning when Professor Jhunjhunwala talked about some of the challenges and setting up, he made a comment that we should be even willing to deploy technologies with 7%, 10% ROI, and that should be something scaled up. But I started my career with energy efficiency, and always the challenge has been, I think there is this notion which has come up that we will only deploy energy efficiency when the payback is 3 years. So on one side, even commercial investments, returns, people are okay with 10%, 12% return. And on the other hand side, when it comes to energy efficiency, always we are looking for solutions with less than 3-year kind of.
Rahul, this is a new concept. We try to develop it. We'll bring down the cost.
No.
First,
In fact, I'm saying
first
that
we
why-
should just work on it.
No, so my question is that why do we put this artificial challenge that we want that 3%? Like, is there something in terms of the messaging? Because this is a common problem I see many times. When we talk about $100 battery, $1 green hydrogen, there are a lot of commercially viable applications which should be done even at $4, $3.
Anyway, the heating
don't
cooling
do- so
problem
same
is less,
heating, cooling,
less problem.
Can we
Any
deploy
other
this?
question,
Others-
comment? Yes, sir. There, I see a hand.
Housing a startup incubated at IIT Madras Research Park. So we build homes inside factories, and all our homes are less than like G+1, and we can do it at scale. Like we have already done 1,000+ projects across India, and the concept we are also looking at building zero energy homes. And since we are doing it modular, we can use the same design principles and ensure uniformity. So I would like to know what are the challenges that we might be facing in the near future, because like most of the energy conservation happens in big buildings like this, and we are tackling the long tail of the construction business, which are like less than G+4 buildings.
I think can be taken up privately during the dinner and all that. Can we?
Sure. Okay.
Architecture, all these things. There is one another technology showcased by Dr. Girija Sharan from IIM Ahmedabad. There's ground coupled heat exchangers, right? Earth tube heat exchangers where the geothermal energy is utilized to cool the buildings. I'm told there are some buildings in Chennai also working in that lines. I'm not sure. I'm not an expert in that area. Maybe some of the experts can throw more light on this.
Thank you. There is one more comment question.
Nowadays, we are facing extreme climate like extreme summer and extreme winter. Is it possible to store those energy? Like in extreme summer, is possible to trap the heat energy, and is it possible to use throughout the year? And same in the winter season, by the architecture of the building, is it possible to store in the building and use it throughout the year?
Long-term energy storage, even for electricity, is very difficult. For thermal, I don't know.
We perceive the heat and perceive the cooling. If you really look at potential of that energy, it's very low grade. It's generally very, very challenging to store low grade energy.
So there is, I think in terms of the heat storage, a lot of times when you are studying architecture, you are taught that you make the walls thicker and it will hold more like heat or cool in terms of like the heating season and the cooling season. But this also happens in terms of scale of hours and not like days or months that we are talking about. At least we are not aware of anything. I will respond to a couple of your question, Rahul. You probably know the answer to this question when you asked it. I think it's energy efficiency, it's always about scale, it's always about transaction costs. And even when you know that the levelized cost of energy, I think for many of these technologies, and when we are looking at demand flexibility and demand response, you stack them up and you know that I think a lot of the energy, lighting and cooling and other things is much lower than storage, but you don't invest, I think, in the kind of infrastructure, sub-metering, measurement and verification, developing capacity of the utilities to actually run this program, settle it, I think, on the same day. So that is definitely part of the problem. I don't have a solution. We want to, I think, work with people like you to actually help solve this thing.
Certainly, MNV cost is never factored into your energy efficiency cost. Unless and until you specifically do that, it's not going to scale.
Yeah, there is one more question.
Yeah, he asked, is it possible to store energy for a long period of time? There is a company in Finland that is storing heat energy in a sand battery. You know, they have built a huge silo where they store sand, and they store the heat in that battery, store in the sand. So similar kind of thing we should do to cool places also.
I want to ask, one, we have in our institute also, there is a fan, which is a huge fan, a fan with about 3 meters kind of blades, and it moves at a very, very low speed. And yet in a large area, open hall, it gives quite good cooling. Can someone explain what that is?
I can take a crack. I did my PhD in thermal comfort, so I think I am well equipped to answer this question. So I think the most important thing is that we are looking at temperature, humidity, and air speed. These are the environmental factors when we are determining the thermal comfort. And what you are seeing is not, I think typically people say that, okay, increase the fan. If it's moving faster, it will give more cooling, but that's not the case. It's the volume of air that gets moved and at what speed it is actually passing onto your skin. So if you have a very large, high-speed air velocity, then you will feel very drafty in cold season, and otherwise I think you'll feel uncomfortable. So it's the right combination of the air speed. And somebody was talking about, we always say that use the set point temperature at 26.7 degrees Celsius and have a low velocity fan, and this is something that Infosys is doing, where when fan went out of business, that, oh, we are a class A commercial building, and we don't want to put fans because it gives like, these are like poor people who use fan. They brought back the fans in their design. And they have this principle of using temperature setting at 27 degrees Celsius and using fans. And Infosys, if you look at 35 million.
They also remove moisture. I think that is a very, very important component.
Right.
If they do not remove moisture, the same thing will be. I've seen that, I've examined that. The key thing is removing moisture. Ankit, you had something to say.
No, so basically this is a big diameter and a low RPM fan, which ensures that a lot of volume of air is being circulated and gives you a thermal comfort. So big spaces, even in airports and all, we have seen this kind of fans getting deployed. So yeah.
I have another question. Again, maybe Satya, maybe others. He mentioned about use of carbon dioxide in kind of refrigeration or cooling as opposed to other material. And he said vis-a-vis vapor compression. What is this carbon dioxide based cooling? What are the challenges? Why is it 5 to 6 times more expensive?
Yeah, I can answer that. We are building the system now. CO2 based cooling is primarily replacing the gas refrigerant that you have with carbon dioxide as the working fluid. The reason why we would like to do it is energy efficiency wise, it's at least about 18 to 20% more efficient than any of these current refrigerants. The other advantage is I can get instant one pass heating or one pass cooling. So any other traditional system, I design for the latent heat from the refrigerant, so I do multiple passes. Whereas in this system, I do what I call as a gas cooler. So I take tap water and I can heat to 95 in a single pass, almost like an instant geyser. The reason why it's, and also the system, the way we have designed it, I don't need multiple circuits. I can go all the way from 5 degree on the chiller side to 95 degree on the heating side. This I cannot do with any kind of vapor compression system. The challenge why it's very expensive is most of the time, the system is under a very high pressure. So it's almost at 130 bar, and also it is manufactured in very low volume. The economies of scale of a vapor compression system does not exist. It is changing. A lot of automotive companies, including Benz, have now started using carbon dioxide based air conditioning system in their cars and EVs. It is changing, but it's a matter of time when the cost goes down. There's also a lot of mandate for CO2 heat pumps in Europe. Also in the US, Los Angeles and the Western Coast, they have started promoting CO2 heat pumps. So I think it's a matter of time before which it starts scaling.
Yes, sir. Yeah. Take another mic. There are multiple mics.
Yeah. So I had a question related to the, I think audience also brought it up, the geothermal cooling. I had a question, is that?
I think the mic is not working, some reason.
Oh, this is working, okay.
Yeah.
There was also a reference to geothermal cooling by one of the audience. I think one of the, I'm going back to the earlier thing on humidity and cooling effect. Is that a good, not alternative, but currently a option as well?
Geothermal or ground source?
Ground sourced, actually. That's why
heat
I mean,
pump,
yeah.
like. Go ahead, Satya.
Yeah, ground source heat pumps, there is a Hyderabad company called Gibbs who have been trying it. It's really good for extracting heat from the ground for a place like say Ladakh where ambient temperature is very low.
Rivers exist for Chennai.
The challenge in the rivers is that the temperature gradient of ground, the ground source in and around Chennai is not that great. Even if I go 9 meters, I don't go below 25, 23 degrees. So it becomes a challenge because the heat exchange and all of that, you don't have gradients.
There is a guy, Arijit Ghosh, who doesn't go like shallow, who goes like 300 feet deep, vertical, and spaced apart, and does the calculation. And he is actually working with the Airport Authority of India right now to design the HVAC system for the Leh airport, which the Prime Minister wants to be zero carbon, both from embodied as well as operational, which is a very, very tall order right now. But they are doing the calculations, they are doing the engineering design, and he has many installations, both in extreme cold and extreme heat, in Iraq, and then in Bhutan, and then in Ladakh.
Any panelists have questions with each other? What I will give then each of you 2 minutes, concluding remarks, and we will end hopefully in time, less than 2 minutes. Start with you.
Yeah, definitely. I think, as I mentioned, there's a lot of problems to be solved. Some of these solutions exist. It needs commercialization. Some of those need technology, material science, etc. So there's a great opportunity for the students and faculty to look at some of the material science, especially in the low power electronics, as I mentioned, or wide band gap like gallium nitride, others, and some of the others in the heating and cooling as well. There are quite a lot of technology. Two problems that the professor posed. So those are all really right solutions, and then go through a very detailed process from ideation, incubation, and then talking to customers and see how you can actually pilot and then scale. The 4-step process that the professor mentioned earlier. So I think that is a good problem to have to do a few things, right? One is reduce the dependence of foreign oil and improve the energy security. Generation will always happen, storage will happen. Energy efficiency is something that can really help reduce the need for generation.
Thank you. Karthik.
Yeah, when you look at the heat consumptions by all of us, we are about 100 watts, and when you're looking at bulbs which are 400 watts, the basic balance is at the higher ends is the geyser around 1500 watts, and the air conditioning is also 1500 watts, and that's exactly where the whole problem started of heating and cooling together. So to me, given the balance more towards cooling, I think it's all about maintaining it, getting the insulation right, and ability for us to have the balance between fresh air and insulation.
So I had a question. In building design today, any building design, is thermal load taken as a primary consideration at the design time?
Ideally, yes, but then...
does that happen? Can that be put as a regulation? Just like architect will not design something if structurally it is not sound, can we design taking thermal thing in consideration?
There is the Energy Conservation Building Code. So there is already a mandate to design the buildings in an energy efficient manner, considering all the external, I think, environmental load as well as the internal load, the people load, equipment load, and everything. And there are very, very advanced tools and simulation programs that can do it for you. So, and this is becoming par for the course. Most of the good architects and environmental design consultants can do this. I mean,
Thank you. Ankit?
No, I would like to end by, just by encouraging all of us that few years back, we were not really understanding what the carbon emissions and all really means. But now we are in a stage that we have started understanding that if inefficient system, how is it impacting the world and how is it impacting our daily lives? And more importantly, the next generations that is going to come. So I think we all have to come together, and mostly all the young engineers sitting over here, how we can make things more better and efficient.
Satya, you have... Yes.
Yeah, so my, I think last message is that I do feel that this conference, which is kind of like looking at the entire energy value chain and the supply and demand, is a really good thing. I'll give one example that we all know about LED success story. There is another success story that India can power. We have 500 million fans and we have 40 million room air conditioners. 40 million is supposed to go to like about 200 million air conditioners. So I think, and we talk about chillers, but the key appliance is room air conditioner. Because so that is going to drive it. Our peak demand is going to go from 50 gigawatt to 200 gigawatt. And that's what the global cooling prize was about.
And better motors.
Yeah.
We have a session on that.
BLDC motors, I just want to come to that. We have 500 million fans, and they are consuming 60 to 70 watts.
Yeah.
We have the technology available right now that can cut it in half. It's a plug and play technology, and it will save about
7 years back we designed it. We have put it in 60,000 homes. Half the buildings in IIT today have the 30 watt phone, all BLDC fans.
And 10 to 15 gigawatt reductions can happen just like it.
Do you want to say something? We want to wind up. It's almost 6:30.
So what I think I would like to put forward is ways for us to work on capstone type projects where we do put out certain large projects, really come together as ISA or the Alliance for Energy Efficient Economy, and really put together to see how do we build such demonstrators and commercially viable. I think that's what we would like to do. And plug and play technologies in there as we go.
Thank you. Yes.
So I had an observation what Rahul asked in terms
Question
of
may be difficult because it's already
Sure, but an observation.
observation we'll take.
Yeah.
Question can be discussed during dinner time.
Sure. So the thing is that we're talking about how do we bring these technologies of energy efficiency when it comes to cooling and heating in our homes, right? I think one of the important aspects of bringing that, at least in India, is to bring the right kind of policy frameworks. For example, when we talk about rainwater harvesting, it became a mandate to install rainwater harvesting in many parts of the country when you are going for a new building construction or new house construction. Unless and until we have some kind of policy mandate to say that, okay, this much amount of load is only allowed per square feet of built up area per home. Because what we are doing is a lot of homes these days, and especially well-off homes, are misusing the affordability of air conditioning and HVAC. And unless and until those mandates can be brought in, none of what we say and new technologies can never be viable, because it's always easier to buy 10 air conditioners and install them.
Thank you, thank you. I want to try to wind up in time. I like to, but we run out of time. We have been delayed since morning, and that's what the impact on this session is. Heating and cooling in industry, because it is industrial heating and cooling which is very, very significant. It is there. We have talked about office buildings, we have talked about homes, we have not talked about industry. And that's another major area where so much can be done. Every industry uses heating and cooling. Some things Satya talked about, particularly talked about the ones which are using below 120 degree or probably 150 degrees centigrade. But there are many other heating and cooling is a major issue in industry, and what can be done, how that can be done can become another thing. I think maybe we require extensive sessions. Probably in future we may have panel sessions for this conference and take up each of these issues in great detail. I want to thank each of the panelists. Fantastic. And Satya, give a big hand to all of them. I think you people want to give some kind of memento. Please go ahead and start giving memento while I ask the students from our partner engineering college to come and meet us in the amphitheater. Thank you. Thank you very much.